Hey, Chem30s, it's Manchak here with your Concept D3 video lesson. If you are reading or watching this video, you should have already completed Concept D1 in this unit, which was a really quick introduction to equilibrium and what equilibrium is all about, and from the context of this unit, which we're looking at chemical reaction equilibrium. And then where you should have completed as well is how to look at concept D2, which is dealing with how we represent chemical reaction equilibria and how we talk about Kc, which is our equilibrium constant. What we're going to do today is we're going to have a look at Le Chatelier's principle. And Le Chatelier's principle is the principle that helps us sort of understand what happens to a chemical equilibrium when we disturb it in some way, if we alter it in some way, shape, or form. So that's what we're going to be looking at today. And I'll just quickly call up for you the concept checklist, and we'll just have a quick look at that so we know what we're doing. So we're going to be able to predict, and the key word here is qualitatively. So we're not putting numbers to this. We're just going to talk about using words to describe or qualities to describe how these changes are taking place. And we're going to use Le Chatelier's principle to predict shifts in equilibrium caused by changes in temperature, pressure, volume, concentration, or the addition of a catalyst, and describe how these changes will affect the equilibrium constant. So I'm going to go through and I'm going to run through these things with you, and hopefully you'll get a better sense as to what we would do in a situation where we disturb a chemical equilibrium in some way. For this concept, we are going to have some videos to watch. I've got two of them I've selected for you. One of them on Le Chatelier's principle, about 4 minutes, 8 seconds long. And then jumping back into our stuff from Crash Course, if you wanted to watch this video from the beginning, you could, or you could sort of jump in where you left off with it last week, or last in Concept D2, no, actually it was last week when you did Concept D1. So whatever works for you, that's fine, but that's what we're working on here. Then there's going to be a line master that I want you guys to do, LSM 15.2J, which is on Le Chatelier's principle. Highly recommend that. And then if you haven't jumped into it already, jump into worksheet 2. So this worksheet 2 is going to cover concepts D2 and D3. So you can jump into this one to prepare yourself for the formative and then the summative quiz afterwards. So I think without further ado, I'm going to jump into the lesson, and feel free to pause at any point if you need to go back and rewind or watch anything again. You're welcome to do that. So I'm going to jump into this, make my video just a little bit smaller here for us to see. So we're going to explain qualitative changes in equilibrium systems. Really, this concept is all about Le Chatelier's principle and what Le Chatelier is all about, and what his principle was used to explain. So in many areas of chemistry and industry, studying the effects of varying system properties on the equilibrium of that system has been essential. It has helped to develop our understanding of equilibrium states. In particular, in industry, what often happens is a chemical reaction will be done, but it won't go to completion. And we now understand that that's because there is an equilibrium that's struck that is, it's not a quantitative reaction under the conditions we put it under. So maybe it favors the reactants, maybe it favors the products, but nonetheless, there is something going on with this particular reaction that prevents it from going complete to completion. And so what we're going to end up doing is industry would often take a reaction like that, and they would fiddle around with it to try to make more product out of it. And so this was some cases a situation where technology has driven science, because they do something to that reaction to get more product out of it, and as a result, they end up improving their reaction. They don't know how it works, right? They're not sure how this process worked, but they know what they did shifted the reaction the way they wanted it to be shifted. So that's what we're talking about here. This is a technology is driving science in this case. So technology manipulated the reactions. They got a favorable result and ran with it, probably because it made them more money. Science followed later to explain how the favorable result took place and why that result took place. So that's the situation we're dealing with there. So the favorable results were necessary for among other things, to create more product more quickly or more completely, or usually in a less expensive way. That's really what industry is all about. It's all about making sure that you minimize the amount of money that you spend on a particular procedure or whatever you're doing. So in order to explain how manipulating a chemical system at equilibrium will change its equilibrium state, we invoke what we call, or evoke, I don't know, you choose, Le Chatelier's principle. And Le Chatelier's principle states that when a chemical system is at equilibrium, it is disturbed. When a chemical system at equilibrium is disturbed by a change in a property of the system always appears to react in the direction that opposes the change until a new equilibrium is reached. So what we're going to see here is that when we disturb a system at equilibrium, it acts to oppose that change. Okay, and we're going to see this from a few different perspectives as we move through this section. So, in other words, if we want to look at it this one way, and if I was you guys, I'd highlight this section in your notes and make sure you're clear on it, because this is an important section for you, and it really tells you what Le Chatelier is all about. Really, what I want you to get is, once a system is at equilibrium, if we unbalance the system, if we change something in that system, then what ends up happening is we end up having the system shift to oppose whatever that change is. So in other words, if we add some of a product, in the equilibrium will shift left towards the reactants to reduce the addition of the products, right? It's going to act to oppose the change. We have more products, so it's going to use those extra products up to make more reactants. Okay? If we want to shift the equilibrium to right to favor the products more, we must either add one of the reactants. So if we add more reactant, what's going to happen is it's going to act to oppose that change by using the reactants or running the reaction in a forward direction in order to make more products, using up the extra reactants to make more products. The other way that this could happen is we could take products away. Okay, so we're going to look at all of these in a second. Think about for a moment about how this is going to affect industry, right? If you want to make more product, maybe the easiest thing to do is just take some product away, right? And then the reaction will continue to shift to try to reestablish that equilibrium that it established before. So here's what we're going to do is we're going to look at Le Chatelier's principle from three perspectives. We'll look at it from the idea of concentration. We'll look at it from the idea of temperature, and so changing concentrations, changing temperatures, and then finally we'll look at it from the idea of what would happen if we mess around with pressure and volume. And remember, pressure and volume are linked, because we talked about it in Chem 20 when we did our gases unit. They're linked to each other, and they're inversely proportional to each other. If you guys recall that would be Boyle's law that described that to us. So we're going to start out first with Le Chatelier and what happens when we change concentrations. There's two things I want you guys to understand, okay? As we go through each of these, understand how the equilibrium is going to shift, right? Is it gonna run in the forward direction or shift towards the products, or is it going to run in the reverse direction and shift towards the reactants? Okay, so be able to tell me whatever little thing we do to it, how is it going to shift? And then the second thing I want you guys to be able to do is to be able to tell me how or why this might work. And that is going to require you guys to have a look at what we call, if you recall, the collision reaction theory and what goes on with that. Okay, so let's talk about concentration. Le Chatelier's principle predicts that the addition of a reactant to a system increases the concentration of that substance. Thus, the system will undergo a shift forward or to the right or to the products in order to oppose that change. Okay, so we're talking about a shift here. In this case, our disturbance is adding a reactant. So that reaction chamber that we have has more reactant in it. If there's more reactant in it, that means that it's going to increase the concentration of the reactants, and Le Chatelier's principle means that the system is going to act to oppose that change. How is it going to oppose that change? It's going to oppose that change by shifting to the right, by using those extra reactants to make more products. Okay, that's opposing the change, because when we use those extra reactants to make products, the reactant level drops again. The concentration of reactants drops again. So basically, we'll see an initial decrease in the reactant concentration as the reactants are turned into product. After this period of change ends, we establish a new equilibrium state, and the system is changed in such a way as to oppose the introduction of the product or the reactant. We could also we can mess with reactants and products in a bunch of concentrations in a bunch of different ways. So we could add more reactant, which is going to shift the reaction to the right as it consumes the extra reactant to make products. We could remove reactant, right, which is going to shift the reaction to the reactant side, make more reactant to oppose that change. We could increase the amount of product, which will also shift the reaction towards the reactants because it's going to react in such a way as to remove products. Or we can remove the products, which is our last way, and that's going to shift the reaction towards the products as well because we're trying to make more products to oppose the removal of the products. I hope that kind of makes sense. Now, I said to you guys before, D3 is a tricky concept. It's a concept that's going to be a lot of work to wrap your head around. And so you need to kind of follow the bouncing ball and watch what is that shift that's taking place and why is it going to shift? Because it acts to oppose the change. If we increase reactants, it's going to act to oppose that by decreasing the reactants. How is it going to do that? It's going to use those reactants to make products. Okay, wrap your head around that if you can. Okay, so there's a wonderful summary on page 691, 692 of your textbook if you wanted to have a look at that. What I'm going to do is talk a little bit about how collision reaction theory explains why this works. Okay, so this is what would happen. That's the first part of this. But why does it happen? That's the second part of this. Okay, so I think this one's relatively easy to wrap your head around. If you, let's say, add more reactant, what's going to happen? Remember, collision reaction theory is all about in order for a reaction to occur, the entities must collide with enough energy in the right orientation for the reaction to occur. If we add more reactant, it means we have more reactants bouncing around in our reaction container. And that means that if there's more reactants around, there is an increased probability of collisions between reactants, an increased probability of collisions with the right orientation and the right amount of energy in order to create products. So what's going to happen is because we've increased the probability of reactants colliding with each other, then it's going to shift forward. Okay. Same thing as if we remove products, right? If we remove products, that means there's more reactants in that chamber. There's an increased probability of reactants colliding with each other, meaning that it's going to shift towards the right, which is going to create more products, okay? What I need you guys to understand is the addition of or removal of a reagent in pure solid or liquid form does not change the concentration of that substance, so equilibrium is not disturbed. So really what we want to look at is the way we increase or decrease is by shifting with respect to aqueous or gaseous entities in that substance or in that reaction that we're looking at. Okay, I hope that makes sense. Remember, the videos that I've included for this are excellent, and I'd really highly recommend that you guys view them, maybe even right after we've done this, to reinforce what I've just talked about. So let's talk about temperature, okay? And there's a lot of different ways to look at temperature. The first thing I want to remind you of, okay, is when we alter temperature in a chemical reaction, when we're talking about a reaction that establishes equilibrium, we are going to alter the equilibrium constant as well. So remember that. This is a qualitative concept here. So you're not going to have to do any calculations related to that. Don't worry about how it's going to change. Just worry about the fact that we're going to change the equilibrium constant. The best way to understand what happens when we deal with Le Chatelier and altering a temperature of a reaction system is to think about the temperature or heat or energy in terms of being a reactant or a product in the system. And so when we're doing these questions, often we will include energy or heat in the reaction equation that we're looking at. So if we look over here, this is a situation where in the forward reaction, it is endothermic. But in the reverse reaction on this one, it is exothermic. Okay, so if we consider this to be a reactant in the forward reaction or a product in the reverse reaction, then what we can do is if we alter, let's say we increase the temperature of the system, all of a sudden we have more energy around, which is going to increase the probability of reactants reacting to form products. So this reaction is going to shift towards the right. I hope that makes sense to you. If we were to decrease the energy, what's going to happen is it's going to act to oppose that change, right? We're going to decrease the temperature, act to oppose that change by making more temperature. How is it going to increase the temperature? Well, it's going to run in the reverse direction so that we can get more of this energy as a product to increase the temperature in the system. Okay? So I want you guys to think of it in that respect. So when you're doing a Le Chatelier question, watch out for whether we've included temperature as or energy as a reactant or product in the reaction that we're looking at. Remember that temperature can sit, or the energy can sit beside the reaction as a delta H, thinking back to Unit A. Remember, if delta H is negative, that means it's going to end up on the product side. It's an exothermic reaction. And if the delta H is positive, it will end up on the reactant side. It's an endothermic reaction in the forward or reverse direction. Okay, so this is basically what I've explained already here down at the bottom, so I'm not going to go into that too much more deeply. But let's just look at a couple of quick examples to sort of see this. So in a salt sulfuric acid process used to produce hydrochloric acid, the system is heated in order to increase the percent yield of the hydrogen chloride gas. So if this is our reaction, notice we've plugged energy in there. Energy is sitting in there as a reactant, so meaning that if we increase the temperature in that system, that reaction system, there's going to be more of this reactant around. Energy is pretending to be a reactant. So there's more of this reactant around, meaning we're going to produce more of the hydrogen chloride as a result, which is one of the goals of this reaction. In the production of sulfuric acid, the key reaction step is the equilibrium represented below. Percent yield of the product is increased at a low temperature. So in this case, what they're doing is they're dropping the temperature of this reaction system. And by dropping the temperature of the reaction system, the whole reaction system is going to shift in the direction that tries to increase that temperature again. Well, that is shifting it to the right or favoring the products more, because that means it's going to produce energy as a product. It will be an exothermic reaction that will try to increase that temperature. So then the next thing I want to talk about is how this relates to Le Chatelier. This temperature thing relates to collision reaction theory and what goes on here. So when you add heat to any reaction, its rate will increase. Thus, a reaction system at equilibrium will see both forward and reverse reactions speed up when heated. The endothermic reaction, which has a larger activation energy, will benefit more from the addition of the heat, so it will speed up more. This will result in a shift to more products of the endothermic reaction. So if we look here, this is your endothermic reaction. And remember, let's rewind for a second. We're talking equilibrium right now, which means that each one of these reactions has an exothermic and an endothermic portion, right? If we're reading this reaction, what the heck is going on here? If we're reading this reaction below here, this is going to be exothermic in the forward direction, but endothermic in the reverse direction. Every reaction is going to be like that. And so we can take that into account. We can make that consideration as we move through. So in the endothermic reaction, which has a larger activation energy, it's going to benefit more from the addition of heat, and it's going to speed up more, right? So what it's going to mean is that when we add more energy, the endothermic side of the reaction, whichever side that is going to use that energy and run in the opposite direction, right? Because it has enough energy to overcome that activation energy. The opposite is true if we take away energy. If we take away energy, there's going to be a better chance of these guys colliding with the right amount of activation energy in order to make products. And so that's going to shift it in the direction of the exothermic reaction. Hope that makes sense. That's probably a really tricky thing to wrap your head around. So maybe listen to this section again. Maybe try to have a look at these and try to understand the activation energy thing. If there's minimal amount of energy around, if we've dropped the temperature significantly, then there's a better chance of the exothermic reaction taking place than if we increase the temperature and we've got enough to reach that activation energy on the endothermic reaction, then there's a better chance of the endothermic reaction doing what it's supposed to do. Okay, I'm almost done here. Let's talk about our last one. So we've talked about what happens if we mess with concentrations. We've talked about what happens if we mess with temperatures. Let's talk about what happens if we mess with pressure and volume. And usually the thing that we're going to mess with here is volume. And remember, please, that they are linked to each other. So if I take a container and I squish that container of gas down to half of what its size was before, its volume is decreased by half. That means I've doubled the pressure. Okay. If I take that reaction chamber and I let it increase to its regular volume, or increase or double its volume, what's going to happen is I'm going to halve the pressure. And that all has to do with the atoms bouncing around, or molecules bouncing around inside that container, and whether they're colliding with each other or not. So the amount concentration of a gas we know is directly proportional to its pressure. Decreasing the volume of a container of gas by half, we know doubles the concentration, but it also doubles the pressure in the container. So we need to consider the total chemical amount of gas reactants versus the total chemical amount of gas products. So we are going to be looking at chemical amount, or number of moles. Remember, we're not dealing with measurements per se in here, but we do have a balanced chemical reaction. And a balanced chemical reaction includes coefficients that are going to tell us relative amounts of reactants and products. So if the volume is decreased, overall pressure is increased. Therefore, we get a shift to the right depending on what our reaction system looks like. So I want to look at this reaction system down here at the bottom. First things first, we cannot do volume or pressure changes and shifting a reaction for anything other than a system that is made of gases, okay? Because gases are the ones that are susceptible to pressure changes, okay? So remember that. So what we would do is, if we look at this reaction system, okay, and if we're talking about a volume and pressure shift, what's going to happen is, if we look at the reactant side here, we've got 2 moles of sulfur dioxide and 1 mole of oxygen gas, giving us a total of 3 moles on the reactant side. There are only 2 moles on the product side here, okay? 2 moles of gas on the product side. So what's going to happen is, if we increase the pressure or decrease the volume of this system, what's going to happen is the reaction is going to shift to favor the products, because it's going to try to undo that increase in pressure. How is it going to? It's going to undo the increase in pressure by taking 3 moles and turning it into 2 moles. That decreases the number of particles bouncing around in the system, which decreases the pressure in that system. Okay, if we do the opposite, if we increase the volume, what it's going to try to do is maintain the pressure it was at before by shifting, in this case, to the left, by increasing the number of particles bouncing around, because it's going to go from 2 particles bouncing around to 3 particles bouncing around, which is going to increase the pressure of that system. So we're trying to reverse the changes that are taking place. Okay, but it only works if our number of moles are unbalanced for some reason. If there are 3 moles on this side and 2 moles on this side, what that's going to mean is it's going to shift depending on what we mess with the pressure. But if there's 2 moles on this side and 2 moles on this side, it's not going to do anything. Okay, so something to consider there. So we explain the result of decreasing volume of a gas system by assuming that both the forward and the reverse reaction rates become faster because the concentration of the reactants and products increase. Whether the reactants or products are favors depends on which side of the reactant has more particles, because it's going to shift to oppose that change by reducing the number of particles to try to maintain that pressure or get back to where it was before. Okay. Oh, I hope I've done a good job of explaining that to you guys. You may want to rewind it. Don't forget to follow or watch the videos as well, because I think this one is going to take a little bit of time to wrap your heads around. And please do some of the practice worksheets, because I think it's really going to help you guys moving forward to do that. One last thing to talk about then is catalysts and equilibrium systems. So a catalyst decreases the time required for each system to reach its equilibrium position, but it does not affect the final position of the equilibrium. Okay, it doesn't affect whether it favors the products or the reactants. It's just going to decrease the time that it takes for us to get to the equilibrium position that it should reach. Remember that catalysts have something to do with the activation energy and lowering activation energy. Okay, so a catalyst lowers the activation energy for both the forward and reverse reactions by equal amounts, so the equilibrium establishes more quickly. The equilibrium it establishes is not different as far as how much it favors the reactants or products based on compared to an uncatalyzed reaction. Okay, so the catalysts just go to help us get to that system or that equilibrium state faster. That's about it. Okay, so this is just a quick summary of what we've talked about. I would encourage you guys to have a look at this or have this handy as you are working your way through these concepts or this concept. Please sit it there, maybe play around with it a little bit, have it sitting there and ready for you as you work your way through the concept. Okay, that is concept D3 done. Like I've said to you guys before, it is probably the trickiest concept of the year. At least it is in my mind, because there's a lot of abstract stuff going on, and it requires you to pull in collision reaction theory to do your explanations and have a decent understanding of what equilibrium is, and then to imagine what's going on in that reaction system as we mess around with changes. A couple of words of warning. A lot of the questions are going to ask you to do multiple things as you're working your way through this. So there may be more than one, especially for a long answer, a non-multiple choice answer, there may be more than one way you can tackle the question. I could give you a reaction equation, but you may be able to talk about pressure and volume and how you could shift the reaction using pressure and volume. Or I could give you guys a question revolving, or you may be playing with concentrations in that particular question. You might, if I communicate energy to you guys in any way in that question, then absolutely you can be messing around with concentrate or with temperatures as well. So there's lots of different ways to tackle these questions, and there might be more than one way to communicate it. So please be aware of that as you move forward. I guess the only other thing to mention to you too is take your time and really watch those videos and pay attention. Maybe rewind this one to a couple of spots and really take the time to try to sort this out. It is tricky to wrap your head around. And like I've said before, this is probably the one concept that I have the most difficulty explaining, even with my 10 plus years of teaching Chem 30. It's the one concept that trips me up every year, and I have to stop and I have to think my way through it, and I almost have to talk it out to myself. So be prepared to do those kinds of things as you move forward in this concept. Okay. If you need any assistance with working your way through these questions, please fire me an email. I'd be happy to help you out. Arrange a Google Meet. We can get together and chat that way, whatever works best for you. But like I said, this is a tricky concept. Okay, so I think that's it. I'm going to wrap it up. Please make sure you do the practice worksheets. I would strongly recommend doing them for both D2 and D3, including worksheet number 2, which has a really good breakdown of these kinds of questions, including some diploma style questions for you guys to look at. After you've done that, do the formative quiz. Please wait for my feedback, and then when I give you the okay, you can do the summative quiz. And I think that's it for this week. So that is concepts D2 and D3 wrapped up for us here in Chem 30. I think that means we only have 4, 5, 6, and 7 left to go in the year, in the course. So well done that you've made it this far. Keep up. Track me down if you have any questions. Stay healthy, and we'll talk soon in concepts D4 and D5.